Today we'll travel back 230 million years to see how our planet was once a realm dominated by giants. Imagine a world where huge creatures roam free, a planet teeming with life forms that are changing the way we think about biology and evolution. The Mesozoic Era was a time of dramatic climate change, an era when life had to constantly adapt to survive. From scorching deserts to verdant plains, the dinosaurs' habitat was constantly changing, profoundly influencing their evolution. These magnificent creatures were not simply victims of their environment. They were masterful adapters and evolved to capitalize on every ecological niche. As we travel back in time, we learn that these creatures were not only part of their ecosystems, but also essential environmental engineers. Their interactions with flora and fauna shaped the world in ways that we continue to discover today. Today we'll delve into the genetics of these ancient titans, exploring the challenges and breakthroughs in extracting DNA from fossils. Each piece of genetic material provides a new clue, a piece of a long-forgotten puzzle that we're just beginning to piece together. From fossilized footprints to the cataclysms that mark their end, the story of dinosaurs is one of survival, adaptation, and ultimate extinction. Join us as we explore the echoes of ancient Earth together, uncovering the secrets of the giants that once ruled our planet. So our story begins with the dynamic climate of the Mesozoic Era. This era, which lasted approximately 186 million years, was a time of tremendous change and adaptation for dinosaurs. During this period, the Earth experienced significant climate fluctuations that affected the diversity and distribution of life forms. The Mesozoic Era is divided into three periods: the Triassic, Jurassic, and Cretaceous. Each period has different climatic conditions that influence the evolution of dinosaurs. During the Triassic Period, the climate was generally hot and dry, with vast deserts stretching across the supercontinent of Pangaea. However, as we move into the Jurassic Period, the breakup of Pangaea led to the formation of shallow seas and a wetter climate that favored lush, green landscapes. Studies show that these climate shifts were caused by a combination of volcanic activity, sea level changes, and variations in the Earth's orbit. For example, the breakup of Pangaea was accompanied by a significant volcanic activity, which released huge amounts of carbon dioxide into the atmosphere. This led to periods of global warming, followed by cooling when volcanic activity subsided and greenhouse gases were gradually removed from the atmosphere by natural processes. Dinosaurs, as the dominant terrestrial vertebrates of the Mesozoic, showed remarkable adaptability to changing climates. The diverse ecosystems that emerged provided niches for a wide range of species. For example, the warm and humid environment of the Jurassic saw the emergence of massive sauropods, such as the Brachiosaurus and Diplodocus, which thrived in the abundant plant life. The Cretaceous Period, the final chapter of the Mesozoic, saw even more pronounced climatic shifts. Increased volcanic activity and the formation of new ocean basins led to a warming climate and rising sea levels. During this period, flowering plants flourished, which in turn supported a new wave of herbivorous dinosaurs, such as the hadrosaurs. A key driver of these climatic and environmental changes was extensive volcanic activity, especially in regions such as present-day northern China. Studies show that volcanic eruptions in the Mesozoic released not only carbon dioxide, but also nutrient-rich ash that fertilized the surrounding land, promoting the growth of plant life and, consequently, the dinosaurs that fed on it. Fossils from this era, especially from sites like the Yanliao and Jiho biotis in China, make a compelling case for how these environmental changes drove the evolution and diversification of life. These fossil sites demonstrate the co-evolutionary link between volcanism and the flourishing of terrestrial ecosystems. The influx of nutrients from volcanic ash created fertile soil, supporting a rich diversity of plant and animal life, and periodic periods of cooling following volcanic episodes helped maintain this biodiversity. So let's move on to the theropods, the ferocious and agile predators of the dinosaur kingdom who represent one of the most diverse and successful groups of dinosaurs. Recent discoveries have shed light on their amazing evolutionary path, showing how these predators adapted to different ecological niches and developed complex behaviors. The evolutionary history of theropods begins with a small, nimble hunter. Early theropods, such as Xelophysis, had slight builds, hollow bones, and sharp serrated teeth. An important evolutionary milestone was the appearance of feathers. These feathers were not originally used for flight, but probably served more for thermoregulation. As evolution progressed, theropods evolved into numerous forms, occupying a variety of ecological roles. One of the most fascinating aspects of their evolution is the transition from small feathered dinosaurs to large predators in the late Cretaceous. This period saw the emergence of the famous giants like the Allosaurus and eventually the iconic Tyrannosaurus rex. Fossil evidence, including footprints and bone remains, indicate that some theropods engaged in complex social behaviors, including gregarious hunting. For example, the discovery of several Deinonychus fossils together indicates a potential cooperative hunting strategy. This behavior may have given theropods an advantage in hunting larger prey. Among the theropods, Tyrannosaurus rex stands out not only for its size, but also for its sophisticated hunting abilities. With its powerful bite force, keen senses, and sturdy build, T-Rex was well adapted to dominate the environment. Studies of its brain structure indicate advanced sensory ability, including an exceptional sense of smell and sight. Recent discoveries in Patagonia have provided new insights into the diversity and distribution of theropods. Fossils from this region, including Megaraptorids and Unenlogione, show a rich spectrum of theropod evolution in the southern hemisphere. These findings attest to their adaptability to different environments and their evolutionary success up to the end of the Cretaceous. The evolution of theropods culminates in their transition to birds. The discovery of feathered dinosaurs, such as the Archaeopteryx, provides a direct link between non-avian theropods and modern birds. But more on that later. Discover the realm of sauropods, the true giants of the dinosaur world. These colossal herbivores, characterized by their enormous size and long necks, dominated the landscapes of the Jurassic and Cretaceous periods. Specimens like the Argentinosaurus and Brachiosaurus are known for their extraordinary body size, often exceeding 88,000 pounds in weight. The body mass of these dinosaurs was several times that of any other land animals, both past and present. The evolutionary trajectory shows a rapid increase in body size early in their history, followed by a plateau when they reach their maximum potential size. The secret of sauropod gigantism lies in their unique growth pattern and physiological adaptations. Histological studies of bones show they grew rapidly, reaching enormous sizes in a relatively short period of time. This rapid growth was facilitated by their highly efficient respiratory system, which included extensive pneumatic air sacs that reduced their overall weight while maintaining large body sizes. Huge amounts of food were required to support such massive bodies. Sauropods were well adapted to herbivory and had long necks that allowed them to reach high and low vegetation without frequent movement of their large body. Different species developed different snout shapes and tooth arrangements that allowed them to process a wide range of plant material from ferns to conifers. Despite their size, they were remarkably agile. Modern biomechanical models suggest that their limb structure and muscle distribution allowed them to move efficiently. Their graviportal limbs, thick pole-like legs, supported their weight, and long tails provided balance. These adaptations allowed them to travel great distances in search of food and water. Some of the largest land animals that ever existed, sauropods played a critical role in ecosystems. Their feeding habits influenced vegetation, and their enormous size likely influenced the landscape by creating paths and passageways in forests. Modern technology allows us to visualize and model physiology in unprecedented detail. Using CT scans and 3D modeling, paleontologists can reconstruct internal structures, allowing us to understand their biology and behavior. The evolutionary journey of these graceful giants is a testament to the power of natural selection and adaptation. From their rapid growth rates to their efficient respiratory systems and unique feeding strategies, sauropods demonstrate the amazing ways in which life evolved. As we continue to learn more about these giants, we gain a deeper understanding of the complexity and diversity of life on our Earth. But let's elaborate on this question. How exactly did these huge creatures move? Dinosaur locomotion has undergone significant changes over time, from the earliest cat-sized bipedal form to massive giants like the T-Rex, and eventually to birds. This transformation is revealed through pioneering research using three-dimensional biomechanical models. Researchers from the Royal Veterinary College and Museum for Naturkunde Berlin have found the movements of early dinosaurs were more similar to those of mammals such as humans than those of birds. Using 13 three-dimensional biomechanical models, they analyzed the function of 35 leg muscles in different dinosaur species spanning almost 230 million years of evolution. The study reveals a significant shift from hip to knee locomotion. Early dinosaurs, similar to today's crocodiles, relied heavily on the muscles of the thigh for locomotion. As dinosaurs, especially theropods, evolved, there was a shift to greater use of the knee muscles, which is characteristic of modern birds. One of the most surprising discoveries was the specialized set of muscle functions in large-bodied theropods. Throughout the early Jurassic, theropods such as the Allosaurus developed more mobile leg joints, which may have been associated with hunting larger prey. This specialization represents an interesting phase of locomotor evolution that did not follow a gradual pattern of more bird-like development. The use of biomechanical models played a crucial role in these discoveries. By scanning key dinosaur fossils into 3D models and reconstructing the muscle attachments based on fossil evidence, scientists were able to model how they moved. Professor John Hutchinson, a leading researcher in the field of evolutionary biomechanics, explains, "This study is a turning point in our scientific endeavor, bringing together fundamental findings from more than 25 years of work. We've been able to examine evolutionary timescales in 13 models of important representative species, opening up new questions about how musculoskeletal biomechanics evolved at the level of 35 individual muscles." But how did the dinosaurs manage to leave the surface of the earth and soar to the heavens? Welcome to the fascinating world of feathered dinosaurs. These structures were also present in numerous dinosaur species, providing crucial evidence of an evolutionary bridge between dinosaurs and modern birds. One of the most significant paleontological discoveries of the past few decades has been the discovery of feathered dinosaur fossils. These discoveries have changed the way we think about biology and evolution. Among the most notable finds are 125 million year old feathers from the dinosaur called Sinornithosaurus and the early bird Confuciusornis, as well as a 50 million year old feather from the United States. A recent study by paleontologists at the University College Cork in Ireland has revealed X-ray evidence of proteins in these ancient feathers, and that shades new light on the evolution of feathers. The team, led by Dr. Tiffany Slater and Professor Maria McNamara, developed a new method to detect traces of ancient feather proteins using X-rays and infrared light. Dr. Slater explains, "We found that feathers from the dinosaur Sinornithosaurus contain lots of beta proteins, just like the feathers of birds today." This discovery confirms that the protein composition of modern feathers was already present in the feathers of dinosaurs and early birds, indicating that feather chemistry emerged much earlier than previously thought. The feathers of modern birds are rich in beta proteins, which help strengthen feathers for flight. The presence of these proteins in dinosaur feathers suggests that these ancient creatures had feathers adapted for a variety of functions, including thermoregulation, display, and perhaps even flight. A study by a team from UCC is helping to resolve a long-standing debate about whether feather proteins can persist for millions of years. The team's experiment showed that while some fossil feathers retain traces of the original beta proteins, others showed signs of protein degradation through the fossilization process. This explains why previous studies of dinosaur feathers found mostly alpha proteins, which was misleading. Professor McNamara notes, "Traces of ancient biomolecules can certainly be preserved for millions of years, but you can't read fossils literally because even seemingly well-preserved fossil tissues undergo changes during the fossilization process. We're developing new tools to understand what happens during fossilization and unlock the chemical secrets of fossils." Feather evolution played a crucial role in the transition from terrestrial dinosaurs to flight-capable avian species. Feather structure evolved from simple filaments to complex flight feathers, with asymmetric blades crucial for aerodynamics. Archaeopteryx, often considered the first bird, demonstrates this transition by combining bird and reptilian feathers. Its feathers were structurally similar to those of modern birds, providing lift and maneuverability necessary for flight. Dinosaurs were not just the inhabitants of their world, they were the architects of their ecosystems. These ancient giants played a crucial role in shaping the environments in which they lived, influencing everything from plant life to the spread of other animals. Using an interdisciplinary approach, we can understand how their interactions with other fauna and flora transform prehistoric landscapes. Sauropods, those long-necked giants, had a significant impact on vegetation of their time. Their feeding habits of ripping leaves and branches off tall trees helped shape the structure of prehistoric forests. The constant eating and trampling by large herbivores led to the evolution of hardier, more resilient plants and may have contributed to the spread of low-growing, ground-covering vegetation. The physical presence of dinosaurs, especially the massive sauropods, altered soil composition and water distribution. Their movements compacted the soil in some places and loosened it in others, creating a mosaic of microenvironments. In addition, the vast amount of plant material consumed by these herbivores passed through their digestive system and was deposited as nutrient-rich manure, enriching the soil and promoting plant growth. In turn, theropods, carnivorous dinosaurs, were not just top predators. Their hunting activities influenced the behavior and distribution of herbivorous species. This predator-prey dynamic created a balance in ecosystems, ensuring that a single species was dominant and that plant life could regenerate. The presence of theropods probably forced herbivores to adopt different survival strategies, such as herd behavior and migration. Dinosaurs also practiced niche building. They modified their environment in ways that created new habitats for other species. For example, the burrows of some dinosaurs may have provided shelter for small animals and insects. Dinosaur interactions were not limited to other dinosaurs. They also coexisted with early mammals, reptiles, and a vast array of invertebrates. These interactions often led to coevolution, where changes in one species led to adaptations in another. For example, the emergence of flowering plants, angiosperm, in the Cretaceous may have been influenced by the dietary habit of the herbivorous dinosaurs, leading to an increase in the diversity and complexity of the plant kingdom. The influence of dinosaurs as ecosystem engineers can still be observed today. Modern ecosystems, especially those involving large herbivores and predators, reflect similar dynamics. Studying these ancient interactions helps us understand the underlying principles of ecology and the long-term effects of species on the environment. Through their interactions with flora and fauna, dinosaurs played a key role in shaping the prehistoric world. But what could have put an end to such a diversity of species that adapted to almost anything? Today we'll revisit extinctions as we explore the dramatic events that changed life on Earth at the end of the Triassic and Cretaceous periods. These mass extinctions were not mere footnotes in history, but crucial events that affected the survival and evolution of dinosaurs. The extinction at the end of the Cretaceous, marked by the Chicxulub impact, was a catastrophe of unimaginable proportions. A comet or asteroid slammed into the Yucatan Peninsula, releasing energy equivalent to billions of atomic bombs. The impact caused forest fires, tsunamis, and a nuclear winter, radically altering the planet's climate. Studies show that this event led to the death of non-avian dinosaurs and a high extinction rate of vertebrate species. But this was not the first time the Earth had experienced such destruction. About 201 million years ago, at the end of the Triassic Period, another mass extinction occurred. This earlier event is less well understood, but it was no less significant. Volcanic eruptions, climatic shifts, and oceanic anoxia likely contributed to the abrupt extinction of species. To understand which dinosaurs survived these apocalyptic scenarios, scientists use advanced statistical models. By studying the history of fossils, they can identify patterns and infer the resilience of different species. Research shows that while some groups of dinosaurs faced high extinction rates, others showed remarkable resilience and adaptability. One of the keys to survival was adaptability. Dinosaurs that could cope with rapid environmental changes had a better chance of surviving mass extinctions. For example, the small feathered theropods showed remarkable resilience. Their ability to adapt to new food sources and climates was crucial. Contrary to popular belief, not all dinosaurs died as a result of these events. Some species, like birds descended from theropods, they were able to survive and thrive in the period that followed. And these survivors laid the foundation for new evolutionary pathways, leading to the incredible diversity of life we see today. After these extinctions, Flowering plants also emerged and changed ecosystems. The new flora provided new habitats and food sources, further diversifying the surviving species. By studying these mass extinctions, we gain insights into the resilience of life and the complex interplay between environmental change and the evolutionary processes. Understanding the past helps us appreciate the delicate balance of our modern ecosystem and the importance of biodiversity in the face of ongoing environmental challenges. After years of study, the mysteries of dinosaur genetics remain elusive. However, despite the fact that millions of years have passed, scientists have made significant progress in unlocking the genetic secrets of these ancient creatures. Advances in the study of ancient DNA have opened new doors to understanding dinosaur biology, although this path is fraught with difficulties. Extracting genetic material from fossils is a careful process and is akin to putting together a jigsaw puzzle with most of the pieces missing. DNA breaks down over time, leaving only tiny fragments. Researchers have to contend with contamination and chemical changes that distort the original genetic code. However, remarkable advances in genomic technology have paved the way for significant breakthroughs. The development of massively parallel sequencing in the early 21st century revolutionized paleogenomics. This technology allows the simultaneous sequencing of many DNA fragments, which greatly increases the amount of genetic data that can be obtained from ancient samples. Hybrid selection in solution is another cutting-edge technique that helps to effectively fish out the right fragments from a complex mixture of degraded DNA. One of the most exciting aspects of dinosaur genetics is its potential to illuminate evolutionary relationships. By comparing the genomes of non-avian dinosaurs with those of birds, scientists can trace genetic changes over millions of years. For example, some genomic features unique to birds can be traced back to their dinosaur ancestors, revealing deep evolutionary connections. However, analyzing ancient DNA is not without its challenges. Allelic phasing, that is, identifying the initial genetic variation in an organism, is critical to understanding genetic diversity and how different species are related. Historically, many studies have overlooked this step, leading to potential inaccuracies. Recent advances are beginning to address this gap by providing more reliable genetic data. In addition, comparative genomics has revealed intriguing patterns in the genomes of reptiles and birds. For example, the high content of certain components in the genomes of some non-avian reptiles, such as the Tuatara, it contrasts sharply with the genomic characteristics of birds and mammals. These differences in base composition are associated with various genomic characteristics, including recombination rates and gene density, providing insight into the evolutionary pressures that shape these genomes. These patterns help scientists understand how different species have adapted to their environments over time. Through the study of ancient DNA, we're gaining a deeper understanding of the biological complexity of dinosaurs and the evolutionary processes that continue to shape life on Earth. As we conclude our journey through the world of dinosaurs, we find ourselves at the Cretaceous-Paleogene boundary, a pivotal moment in Earth's history. About 66 million years ago, a massive asteroid impact radically changed the Earth's climate. The collision caused unimaginable forces that led to forest fires, tsunamis, prolonged darkness due to dust and ash particles in the air. These catastrophic events led to the extinction of about 75% of Earth's species, including the last non-avian dinosaurs. However, the story of survival and extinction reminds us that although our planet faces unimaginable catastrophes, life finds a way to adapt, evolve, and thrive in the most challenging environments. From the ashes after the extinction of the dinosaurs, the mammalian area grew, eventually leading to the diverse ecosystems we see today. The Triassic Period, which took place around 252 to 201 million years ago, marked the beginning of the Mesozoic Era, also called the Age of Dinosaurs. This was the period between two devastating mass extinctions that wiped out countless species and had a profound effect on the evolutionary processes on Earth. Imagine the fear and uncertainty that must have permeated the planet at a time when so many organisms struggled to adapt and survive in the face of a huge environmental change. And yet, despite these challenges, the Triassic Period eventually played a pivotal role in shaping the world as we know it. A new era began with the Great Dying, also known as the Permian-Triassic Extinction. This was a major event that took place about 252 million years ago, at the end of the Permian period and the beginning of the Triassic period. It's considered the most significant mass extinction in Earth's history, with an estimated 96% of marine species and 70% of terrestrial species going extinct. But it was a blessing in disguise. This event paved the way for the emergence of dinosaurs and other new animals in the Mesozoic Era. The exact cause of the extinction is still not fully determined, but it is believed that it was due to a combination of factors including volcanic activity, impact from meteorites, and a sudden change in the Earth's climate. Some scientists believe that the extinction event was triggered by a mass release of methane, a greenhouse gas from the ocean floor, which in turn prompted a rapid rise in global temperatures and resulted in widespread environmental change. The Great Dying had a profound effect on the evolution of life on Earth, which is what happens every time biodiversity declines. It causes something called adaptive radiation. The concept of adaptive radiation has played a significant role. The dry and warm climate, along with the breakup of the Pangaea supercontinent and the formation of the Panthalassa superocean, posed new challenges and presented new opportunities for evolution. So what is adaptive radiation? Adaptive radiation is the way different species evolve from a common ancestor. It occurs when a group of animals or planets enter a new habitat, or when a new ecological environment becomes available. As the animals and plants adjust to their new home, they may change and become different species. This process can take place over a relatively short period of time and is considered a significant driving force of evolutionary diversity. In other words, those who survived it had a whole new world with a range of ecological niches that needed to be filled. At the same time, there was practically no competition. In absence of competition, the rate of evolution increases. Once certain niches are filled, the evolutionary process slows down again. Mutations continue to occur, but since ecosystems are already occupied by other species, non-competitive species have no chance due to natural selection. One of the classic examples of adaptive radiation is the evolution of cichlid fishes in the Great Lakes of Africa, which resulted in over 3,000 species. These fish evolved into a variety of species, each adapting into their own niche in the lacustrine environment. Some cichlid species adapted to feeding on algae, while others adapted to eating insects or similar small prey. Most remarkably, the first dinosaurs appeared during the Triassic Period, which quickly turned into a wide variety of different life forms, becoming the dominant land animals at the time. However, this was not always the case. Early species of dinosaurs were small bipedal creatures, similar in size and appearance to the modern lizards. Their diversity and evolution continued to expand through the Mesozoic Era. There were other groups of animals that were exposed to adaptive radiation, for example, the first birds, snakes, crocodiles, amphibians, and the first mammals. Early mammals were small and mostly nocturnal, living in the shadow of the dominant dinosaur species. This laid a good foundation for the diverse life forms that would flourish in the Mesozoic Era. During the Triassic Period, a group of reptiles known as Archosaurs evolved. These animals are also known as ruling reptiles because they dominated the terrestrial ecosystems of the Mesozoic Era. Some of these Archosaurs were dinosaurs, the animals that most people think of when they hear the word Archosaur. However, there were other groups of Archosaurs that emerged during the Triassic Period, such as crocodiles, pterosaurs, and therapsids. For simplicity, we often refer to all Archosaurs as dinosaurs, although that's not entirely accurate. The reason we do this is because the term dinosaur is a well-known term used to describe a group of animals that the general public are familiar with. By using the term dinosaur, we can easily convey to the viewer the general time period and ecological context in which the animals existed. So during the Triassic Period, dinosaurs evolved into a wide variety of forms and occupied a wide range of ecological niches, from herbivores to carnivores, from terrestrial to aerial. These adaptations allowed them to dominate and flourish during the Mesozoic Era. Let's start our 51 million year tour with herbivorous dinosaur species. First of all, some of the most recognizable species were the majestic sauropods, long necks and large bodies perfectly adapted to be able to reach the foliage of a. These giants had small peg-like teeth that were ideal for crushing tough plant fiber. But not all herbivorous dinosaurs were as big as sauropods. Take the stegosaurs that roamed the Earth during the late Jurassic Period, for example. With their characteristic rows of armored bone plates and spines, as well as long, sharp spikes on their tails, they had a very formidable appearance. This must have provided them with protection from predators. Scientists believe that the Stegosaurus had a tiny brain the size of a pea, and it was located at the base of their spine. The eyes, on the other hand, were located on the top of the head, which possibly allowed them to see predators approaching from all sides. Other herbivorous dinosaurs were pretty small in size. Compact, agile, bipedal heterodontosaurs lived during the early Jurassic, and due to their size, they could hide in the thickets. With strong legs and a long tail, these dinosaurs were well adapted to a terrestrial lifestyle. They also had a combination of sharp, cutting, and grinding teeth that allowed them to feed on a wide range of food. Their varied diet included both plants and insects. And let us not forget the Ceratopsian, one of the oldest herbivorous dinosaurs. They were large herbivorous dinosaurs. Some of their remains date back to the Cretaceous period, so it seems they were able to survive the Great Dying. They ate a herbivorous diet and were well adapted to a terrestrial lifestyle with strong legs and thick armored bodies. Many of the Ceratopsians had elaborate head ornaments and horns. They were used to intimidate enemies or to establish dominance in their social groups. Obviously, herbivorous dinosaurs spread seeds and fertilized the soil with their droppings, which helped ecosystems to form. They also acted as food for other animals, such as carnivorous dinosaurs, who relied on them for their livelihood. But let's take a closer look at which species could afford to eat another dinosaur. Let's move on to the second group of dinosaurs, the carnivorous species. One of the best-known groups of carnivorous dinosaurs of the Triassic Period are theropods, which include species such as the Eoraptor and Dilophosaurus. Theropods were typically carnivorous or omnivorous, with long, sharp teeth, strong, agile bodies, making them excellent hunters. Many theropods also had grasping hands with sharp claws, and that enabled them to grab and kill their prey. Some theropods, such as the Tyrannosauridae, were the largest predators in their ecosystem, being at the top of the food chain. The largest species was Tyrannosaurus rex, one of the largest known terrestrial predators, measuring up to 40 feet in length and weighing between 8 and 14 tons, according to modern estimates. Their dietary buddy, the Allosauridae, was also fairly large carnivorous dinosaurs with rather powerful jaws, but not quite as powerful as the Tyrannosauridae. Some allosaurids were notable due to the fact that they had a crest on their head and back. For example, the Acrocanthosaurus. Other theropods, such as the pterosaurs, completely adapted to the aerial lifestyle and had wings that allowed them to fly and hunt for prey from above. Some predators were much smaller. The Herbivorous that lived in the early Jurassic period were no more than 13 feet long. They were agile predators that preyed on small and medium-sized animals. They would wait for their prey near small bodies of water, or they ate what was left over from larger dinosaurs. But danger awaited creatures that could not stand up for themselves, not only on land but also in water. Another group of carnivorous dinosaurs of the Triassic period are the phytosaurs, and they lived in rivers and swamps. Phytosaurs had long, narrow snouts and sharp teeth, making them well suited for hunting fish and other small aquatic prey. Despite the great similarity in appearance and lifestyle, phytosaurs are not true relatives of crocodiles. During the rainy season, small rivers and lakes expanded significantly, attracting a variety of animals. The dinosaurs of the Spinosauridae family often lived near water bodies. They also had long, narrow muzzles and sharp teeth for hunting fish, but completely different body proportions in contrast to phytosaurs. Very notably, many Spinosaurids also had large spiny ridges on their heads and backs, much like a ship's sail. There's still no consensus on what role those crests played, but some theories suggest they could have been used for mating or protection. In general, carnivorous dinosaurs were very useful in controlling the population of herbivorous dinosaurs and other animal species, therefore helping to create a balanced ecosystem. Our third stop brings us to omnivorous dinosaurs. Omnivorous dinosaurs were the species that adapted to a diet that included both plant and animals, allowing them to take advantage of a wide variety of food sources in their environment. One of the best-known groups of omnivorous dinosaurs of the Triassic period were the aforementioned theropods. Most theropods were carnivores, however, some species may also have been foraging or supplementing their diet with plant matter. Another group among the omnivorous dinosaurs of the Triassic period were Ornithischia. Ornithischia were generally herbivorous, but some species may have been omnivores. They fed on a mixture of plants and small animals. These included species such as the Heterodontosaurs, Pisanosaurus, and Dryosauridae. In general, they were small bipedal dinosaurs, slightly larger than a dog, having a mixture of sharp cutting and grinding teeth, allowing them to feed on a wide range of foods and thus help them survive in difficult times. With such a wide variety of predators, some species had to search for new habitats in order to survive. Some dinosaurs, such as the Ankylosaurus, adapted to a burrowing lifestyle and lived underground. These dinosaurs had armored plates on their bodies that provided protection from predators. Their short, stocky legs made them great at digging, and interestingly, this species had a club-shaped tail, which it may have been used as a weapon for self-defense. The small bipedal dinosaurs from the Silosauridae family of the late Triassic and early Jurassic periods were also representatives of burrowing dinosaurs. They likely used their sharp claws and powerful muscles to dig holes and create underground layers where they could hide from predators and escape the extreme weather conditions that ravaged their world. Have you ever wondered what it's like to be a tree-dwelling dinosaur? Well, during the Triassic period, some dinosaurs adapted to life above ground, not unlike modern birds. One of the most famous groups of arboreal dinosaurs of the Triassic period were the Drepanosaurus. These small, mobile dinosaurs were only about 20 inches in size and lived throughout the late Triassic and early Jurassic period. Drepanosaurids had long, slender bodies and short, powerful legs, making them well suited for climbing and traversing trees. They had a unique skeletal structure that allowed them to move their arms and legs in a similar manner to modern birds. At the same time, Drepanosaurus had a set of bizarre, almost chameleon-like skeletal features. They likely used their sharp claws and strong muscles to climb trees and move along branches where they could find food and shelter. There was another group of tree-dwelling dinosaurs, the Scansoriopterigidae. These small, feathered dinosaurs lived during the late Jurassic and had long, flexible tails that helped them maintain their balance while climbing and moving in the trees. Additionally, Scansoriopter rigids had a row of long skinny fingers with sharp claws that enabled them to cling to tree branches and other objects. It is believed that Scansoriopter rigids may have even been able to glide through the air flying between trees, which in turn means that flight did not originate bottom up, when terrestrial theropod dinosaurs gained the ability to fly, but instead it may have developed top down, where Archosaurs acquired feathers. As life flourished on land, it also raged in the aquatic environment. Aquatic dinosaurs adapted to life in the water and could live in a variety of aquatic habitats, from shallow rivers and swamps to deep ocean water. One of the best-known aquatic dinosaurs of the Triassic period were the Ichthyosaurs, a species of marine reptiles that resemble modern dolphins in appearance. Ichthyosaurs had streamlined bodies, flippers, and a dorsal fin, making them well-suited for swimming and hunting in the open ocean. Ichthyosaurs had sharp teeth, and they were likely predators, feeding on a variety of marine animals, including fish and cephalopods. The Ichthyosaurs shared the seas with the Sauropterygia, a diverse family of marine reptiles. They came in a wide variety of shapes and sizes, from small, agile swimmers to large, slow-moving predators. The Sauropterygia had a unique respiratory system that allowed them to extract oxygen from the water using their gills. Some Sauropterygians, such as Plesiosaurs, had complex gill structure that was supported by a series of small bones, while others, such as the Nothosaurus, had simpler gills that were supported by the walls of their throat. This allowed the species to leave the land in favor of the ocean water with their abundance of food sources. Another group of aquatic dinosaurs in the Triassic period were the Plesiosaurs. They were marine reptiles with long necks, short tails, and large paddle-like limbs. Some of these giants were up to 65 feet in size. Plesiosaurs were well adapted to swimming, which made them efficient at hunting prey in the water. Large species of plesiosaurs fed on a variety of marine reptiles, including other plesiosaurs, sharks, and other large prey. Some plesiosaurs would sometimes catch flying pangolins, one of the long-necked plesiosaurs discovered by paleontologists that was preserved in the remains of its last meal in its stomach, which included the corpse of a flying lizard, fish bones, and an ammonite shell. Plesiosaurs also shared the vast seawater with smaller reptiles such as thalattosaurs, and they lived during the late Triassic and early Jurassic periods. These species also had long, slender bodies and paddle-like limbs. They reached a maximum of 10 feet in length. Thalattosaurs were likely predators that fed on a variety of small marine animals, including fish and cephalopods. An interesting thing about thalattosaurs was their unique way of hunting. They used their long, flexible neck to attack prey from a distance, utilizing their sharp teeth to grab and hold prey. There were also semi-aquatic reptiles, such as the Nothosaurus. They lived in the late Triassic and early Jurassic periods. Nothosaurus had a long and flexible body with webbed limbs that could be used for both land locomotion and swimming. This made them well suited for navigating and hunting in shallow water. They had a row of small, sharp teeth arranged in a sieve pattern that helped them filter small prey out of the water. In general, the ecological niches occupied by different types of dinosaurs during the Triassic period were very diverse, as were the species that inhabited them. This is clearly reflected in the wide range of physical adaptations that allowed creatures to thrive in such a wide variety of habitats. The end-Triassic extinction, also known as the Triassic-Jurassic extinction, was a major event that occurred about 201 million years ago, marking the end of the Triassic and the beginning of the Jurassic periods. This event is considered one of the 5 major mass extinctions in Earth's history and, like others, it had a significant impact on the evolution of life on Earth. In short, this event was the result of several factors combined. One of the theories about the cause of the Permian mass extinction is that it was the result of the formation of the supercontinent Pangaea, which could have caused changes in ocean circulation and climate. As the continent formed, Earth's climate became more arid. The formation of the new continent was accompanied by a huge seismic and volcanic activity, which could also lead to the release of large amounts of greenhouse gases into the atmosphere and cause a rapid increase in global temperatures. This theory is supported by the presence of large volcanic eruptions and extensive lava flow in the mountain records from the period. But no matter what we assume about its causes, about 3/4 of all animal species that existed at the time died out on planet Earth once more. And this event once again provided an opportunity for the development of new species. This time, dinosaurs will take lead among all other animals. In our next video, we'll tell you how they survived and what fate awaited them in the future. "201 million years ago, the world was plunged into darkness. The great Triassic-Jurassic extinction swept through the planet, destroying countless species that lived peacefully on Earth at that time. Just imagine this time of chaos and destruction, a turning point in the history of our planet, a time when 3/4 of all animal species perished, leaving a barren world behind. But from the ashes, a new world arose, where dinosaurs roamed the land, sea, and sky. They were the guardians of a mysterious and wonderful world that was just starting to unfold, the guardians of a new time known as the Jurassic Period. This time, dinosaurs will dominate over all other animals. Although the exact timeline of their evolution is unclear, it's estimated that dinosaurs first emerged in the late Triassic and dominated the world for over 160 million years. These ancient creatures presented as various reptile groups that adapted to different environments, like herbivores who developed to a large size to reach the foliage, carnivores who evolved to have sharp teeth and claws to hunt prey, and aviary dinosaurs, which had wings. Various adaptations allowed dinosaurs to occupy a wide range of habitats and ecological niches, which made them great contenders for the available resources. The success of dinosaurs in the Jurassic can be attributed to several factors, including their ability to reproduce quickly, their adaptability to changing environmental conditions, and their tendency to live in groups. There are several theories that explain the evolution of dinosaurs during the Jurassic Period. Some scientists believe that dinosaurs evolved from a group of reptiles called Theropods, while others argue that they evolved from reptiles known as Archosaurs. Regardless of their exact origin, it is certain that the number of dinosaurs grew rapidly and diversified into a wide range of species, leaving their mark on the world as one of the most successful and resilient creatures in the history of planet Earth. Let's start our journey through the Jurassic Period with sauropods, the giants that were roaming the Earth in search of food at the time. These massive herbivores, reaching up to 100 feet in length, were a truly wonderful sight. They were among the largest land animals to have ever existed. Despite their size, they were herbivorous animals that fed on vegetation using their peg-like teeth. Sauropods have been the subject of attention among many paleontologists, and their fossils have been found all over the world. One of the representatives of the Sauropodae family that lived in the late Jurassic period was the Apatosaurus. These dinosaurs were characterized by long necks and tails, large bodies, and small heads. Apatosaurus was a herbivore that could grow up to 75 feet long and weighed over 30 tons. Its long neck allowed it to reach the tallest trees, which allowed it to feed on leaves and branches, while its massive body was supported by strong pillar-like legs. One of the most notable features of Apatosaurus was its whip-like tail, which could have been used for defense against predators. Some paleontologists believe that Apatosaurus used its long tail to signal other members of the group, while others believe it was used to scare off predators. Apatosaurus was one of the most common sauropods in North America. The fossils of this species have been found in several locations in the western United States, including Colorado, Oklahoma, and Wyoming. Translated from Greek, its name means deceptive lizard. This is a reference to early paleontologists who originally thought that the bones belonged to a different type of dinosaur. Despite its large size and presence, Apatosaurus remains one of the least known dinosaurs. Another representative of the sauropod group is the Diplodocus. This genus of dinosaurs inhabited North America during the late Jurassic Period, around 145 to 156 million years ago. It had a long neck and a whip-like tail. Diplodocus was one of the longest dinosaurs that we know of, reaching a length of up to 100 feet. Diplodocus had a small head with a narrow, elongated snout and a jaw filled with spike-like teeth, suggesting that they were herbivorous. They are famous for their distinctive tail, which consisted of 80 vertebrae and may have been used for balance, protection, or even used as a weapon. Despite their large size, Diplodocus were relatively lightweight due in part to thin bones and air-filled cavities. This allowed them to move more easily and efficiently than other sauropods of this size. Diplodocus was first discovered in 1877 by paleontologist Othniel Charles Marsh, who named the genus after the double-beam chevron bones using Greek terms for double, diplos, and beam, dokos. Diplodocus fossils were found in the Morrison Formation. That's a geological formation in the western United States that was a key site for dinosaur discoveries in the late 19th and early 20th centuries. Today, Diplodocus remains one of the most recognizable and popular dinosaurs, with casts and models of this dinosaur present in many museums and exhibitions around the world. Along with the large herbivorous sauropods, there were carnivorous dinosaurs, ferocious hunters that relied on the consumption of other creatures for their survival. It was a delicate balance, with peaceful giants and voracious hunters playing their parts in the great ecosystem of the ancient world. Theropods were an impressive group of carnivorous dinosaurs that once roamed the earth as the very embodiment of fear and power. Equipped with massive jaws full of razor-sharp teeth, these apex predators were at the top of the food chain and dominated the Jurassic ecosystem. Despite their diversity in size and shape, theropods showed no mercy when they hunted their prey. Their impressive speed and agility made it easy for them to deal even with the strongest creatures, leaving those who got in their way no chance to escape. Theropods are a testament to the ferocity of prehistoric life and the complex balance of nature during the Jurassic. Allosaurus was a large theropod dinosaur that lived during the late Jurassic, about 156 to 145 million years ago. It was one of the most dominant predators of its time, living in North America, modern-day Portugal, and possibly Africa. Allosaurus was a bipedal dinosaur with a huge body and powerful legs. It had a distinctive skull with large, sharp serrated teeth and a deep jaw for powerful bites. Paleontologists estimate that it reached up to 32 feet in length and weighed between 2 and 5 tons. It was an efficient hunter with long hind limbs and a flexible body, perfect for quick movements and sharp turns. The forelimbs were much smaller than the hind limbs. Additionally, this dinosaur had 3 fingers with sharp claws on each hand. Allosaurus became known thanks to several well-preserved skeletons found in North America, including the famous Big Owl specimen from the Morrison Formation in Wyoming. Scientists have been able to learn a lot about its anatomy and behavior from these fossils, including the fact that it was a solitary hunter that relied on its keen senses and physical ability to capture prey. It is believed to have preyed on other large dinosaurs such as sauropods and stegosaurus, since some fossils of the aforementioned dinosaurs have been found with bite marks that match the Allosaurus teeth. Ceratosaurus was another theropod dinosaur that gave the name to the entire Ceratosauria family. Ceratosaurus was one of the first identified members of that dinosaur group. They were characterized by a unique horn-like structure on their snout that varied in size and shape between the species. A They were also known for their large, sharp teeth and strong skulls. Some Ceratosaurus had short, deep skulls with small brains and powerful jaw muscles, while others had longer, thinner skulls with longer muzzles. Ceratosaurs were carnivorous dinosaurs that likely preyed on other dinosaurs and small mammals. They lived in a wide variety of habitats, including forest, deserts, and savannas, and could be found all over the world. Ceratosaurus species range from small, agile hunters, such as Ceratosaurus and Proceratosaurus, to larger, more robust animals living in later periods, such as Carnotaurus and Abelisaurus. Despite the variety of adaptations and body types, all ceratosaurs had common origin and were closely related to each other. Today, Ceratosaurus are considered one of the most intriguing dinosaurs of the Mesozoic era. While theropods roamed around Jurassic World and kept its other inhabitants in fear with their mere presence, a new player appeared on the scene. This new breed of dinosaur was unlike any other, with an arsenal of defenses that allowed them to stand their ground even against the most ferocious hunters. Not only were they unsuitable as their prey, they were also a serious handicap to their hunting tactics. Stegosaurus, with their unique bony plates and spines, were some of the most recognizable dinosaurs of the Jurassic Period. These herbivorous dinosaurs led a peaceful life, roaming the land in search of vegetation in order to feed. Despite their relatively small size and slow movement, they were heavily built and could use their bone plate and spine to defend themselves against predators. Stegosaurus played one of the key roles in maintaining balance within the Jurassic ecosystem, consuming large amounts of vegetation and distributing seed. These ancient creatures are a testament to the diversity of life that existed during the Jurassic Period. Hesperosaurus were a remarkable genus of Stegosaurus dinosaurs that lived about 150 million years ago during the late Jurassic Period. They were first described in 2006 when their fossils were found in the Morrison Formation in western North America. The dinosaur was a large quadrupedal herbivore. It was also a heavily armored dinosaur with large plates on its back, spikes on its tail, and small bony plates on its arms, hips, and legs, which were used for body temperature regulation and protection against predators. About 20 feet long and weighing up to 1,500 pounds, Hesperosaurus were a true force of nature, with a bulky body and a small head that resulted in a very distinctive appearance. Their forelimbs were short and stout, while their hind limbs were longer and leaner, which allowed them to move easily across the prehistoric landscape. They had a long, stiff tail and small head with a beak-like mouth. The unique spikes on their tail were long and wide, running in 2 rows. These spines were likely used for defense, helping to protect these dinosaurs from predators. Additionally, the spikes may have been used to attract mates or scare off rivals. The exact diet of Hesperosaurus dinosaurs remains a mystery, but they're believed to have fed on low-lying vegetation like ferns and horsetail, using their beak-shaped mouth to cut through the vegetation. Despite its relatively recent discovery and ongoing debate about its precise classification, it is usually counted as a primitive Stegosaurus, closely related to the other dinosaurs in the group. Kentrosaurus was another member of the Stegosaurus dinosaur group that lived during the late Jurassic, about 156 to 145 million years ago, in the savannas of the African continent. Kentrosaurus were a relatively small species with a compact, stocky body supported by 4 legs. The front legs were shorter than the hind legs, which gave the animal a slanted posture similar to its relatives. Kentrosaurus were about 20 feet long and weighed around 1.5 tons. Despite their relatively small size, they had spiked armor that ran in 2 parallel rows along their back, consisting of large bone plates as well as smaller spikes protruding from their thighs, tail, and neck. These defensive structures scared off predators as well as protected the vulnerable lower abdomen of the Kentrosaurus. In fact, the armor is the reason the dinosaur was given its name, meaning prickle lizard. That's in reference to its sharp bone spikes, some of which could be over 20 inches long. In addition to the bone armor, Kentrosaurus are also known for their distinctive skull. They had a narrow skull with large triangular teeth that were perfectly designed for cutting through rough vegetation. They also had a large, bony brow ridge that protected their eyes from the branches of the trees and shrubs that they fed on. With the landscape of the Jurassic constantly changing, the evolution of dinosaurs continued. While the Stegosaurus sported their bony armor as a weapon against predators, a new breed of herbivorous dinosaurs, the ornithopod, emerged. Ornithopods were a diverse group of bipedal dinosaurs that inhabited various regions of the globe during the late Jurassic. Due to their flexible and varied diet, these herbivores were some of the most numerous and successful dinosaurs of their time. They were characterized by a light and agile body, which allowed them to outmaneuver larger predators and efficiently forage for food in their surroundings. Despite their generally small size, they were highly adaptable, varying greatly in anatomy and diet depending on particular species and environment. Camptosaurus were a genus of herbivorous ornithopod dinosaurs that lived during the late Jurassic period, about 155 to 145 million years ago. They were first identified in 1879, when the remains of this dinosaur had been found in what is now North America and Europe. Camptosaurus was a large dinosaur reaching 26 feet in length and weighing up to 1,700 pounds. It had a long neck, a large head with a beak-like snout, and a massive body. Its hind legs were much longer than its front legs, giving it a distinctly forward-leaning posture. Camptosaurus had a number of distinctive physical characteristics that set it apart from other ornithopod dinosaurs. It had a long, narrow head with large forward-facing eyes and a mouthful of sharp, serrated teeth. Its body was relatively stocky with a broad, barrel-shaped chest and short, powerful legs. The feet were equipped with strong, hook-like claws that were used to cling to the ground while scavenging for food. Camptosaurus was primarily herbivorous and adapted to eating low-growing vegetation. Its beak-shaped snout was ideal for trimming tough leaves and stems, and its complex jaw muscles allowed it to easily grind the plant material. It is believed that they lived in groups and roamed the lush Jurassic forest in search of food. Another representative of the ornithopod dinosaur, Dryosaurus. They lived at the end of the Jurassic period, about 155 to 145 million years ago. This was a small bipedal herbivore perfectly adapted to the arid and seasonal habitats of present-day North America and Europe. Dryosaurus were characterized by long, thin legs and a tail that helped them maintain balance and move quickly. Their long neck and small head allowed them to reach vegetation at ground level or low shrubs. Dryosaurus had large, flat teeth that were ideal for chewing through tough vegetation, and their jaw structure was specifically designed for processing plant matter. One of the most notable features of Dryosaurus was their lightweight construction, which allowed them to be fast and agile. Their hind legs had a unique joint structure that provided increased agility and stability. This was essential for escaping large predators such as the Allosaurus, which would pose a huge threat to Dryosaurus in its natural habitat. Their body was supposedly covered with feathers, which helped them regulate temperature and adapt to various habitats and climates. Today, Dryosaurus remains an important part of the fossil record, providing valuable information about the evolution of ornithopod dinosaurs in late Jurassic ecosystems. As the Jurassic period unfolded, a new group of creatures took to the skies. The ornithopods continued to thrive on the ground, but now they shared the landscape with the majestic pterosaurs, who, thanks to their powerful wingspan, became the masters of the skies. Pterosaurs, also known as pterodactyls, were flying reptiles that dominated the skies of the ancient world of the Mesozoic Era. Their fossils have been found on every continent, and they came in a wide range of shapes and sizes, from small and agile to large, and intimidating. These creatures had light skeletons and leathery wings which allowed them to soar through the air with ease. With wingspans that could reach up to 40 feet, pterosaurs were masters of airspace, gliding and soaring with grace and power. Since they came in a range of sizes and shapes, pterosaurs occupied a wide variety of ecological niches, from the sky above the oceans to the deserts and ancient forests. Despite their uniqueness, the exact nature and extent of their flying ability, as well as their relationship to other dinosaurs, remains the subject of ongoing scientific debate. Dimorphodon was a genus of early pterosaurs that roamed the ancient world 201 to 175 million years ago during the early to middle Jurassic. It was first described by the English paleontologist Richard Owen in 1859, being one of the first pterosaurs to be scientifically defined and named. It was a relatively small dinosaur with a wingspan of approximately 3 to 4 feet, making it one of the smallest members of the pterosaur family. But what Dimorphodon lacked in size, it made up for with impressive features. Dimorphodon was a predator species known for its long, narrow jaws and sharp teeth, which were well suited for catching small prey like insects, reptiles, and small mammals. It had wings made of skin stretched between long, bony fingers, as well as short and strong legs with large claws. The species lived in coastal regions near the sea and depended on thermal air current and ocean current to stay aloft for a long period of time. Despite the fact that the Dimorphodon fossils are rare, they've been found in England, Portugal, and Germany, which means it must have had a fairly common species around the world. Another genus of long-tailed pterosaurs, Rhamphorhynchus, inhabited Earth around 150 million years ago. They were a small pterosaur with a unique beak riddled with needle-like teeth, long jaw bones, and a diamond-shaped skin flap known as the uropatagium, and that connected its legs and tail. This structure provided additional surface area for flight and allowed the Rhamphorhynchus to make sudden changes in direction and altitude. Their wingspan reached 6 feet, making it one of the smallest pterosaurs of its time. Rhamphorhynchus was a highly specialized flyer designed for gliding and soaring through the air in search of fish, insects, and other small prey. They had a long, slender body, a small, light skull, and it allowed them to deftly maneuver in the air and make quick and agile turns. Their long tail was reinforced with a series of bones and was likely used for stability and control during flight. In addition to the aerial ability, Rhamphorhynchus is also notable for their well-preserved fossil records. Many complete skeletons have been found in the fossil-rich sedimentary rocks of Europe and Africa, making it one of the most famous pterosaurs from the late Jurassic period. Their fossils provide vital information about the evolution of flying creatures and the ecology of these ancient airborne reptiles. The Jurassic ended approximately 145 million years ago. Although some species disappeared during this time period, nonetheless, it did not feature a mass extinction of dinosaurs. A possible explanation for the extinction of certain species is the competition with new species. As the landscape changed, new reptiles, mammals, and dinosaurs emerged, pushing existing populations out of their habitats and forcing them to compete for resources. These new species better adapted to the ever-changing conditions. They defeated the weaker dinosaurs in competition for food and habitat, resulting in a decline of those populations. Another factor was the change of common flora. During the Jurassic, conifers and cycads were the predominant types of vegetation, providing dinosaurs with an abundant source of food. However, as the climate changed and temperatures rose, a new type of vegetation began to develop: the primitive flowering trees. This change was accompanied by a decrease in available food sources, which led to a decline in dinosaur population. As a result, some species could not adapt to the new environment and became extinct, while others were forced to evolve in order to survive. Many people mistakenly believe that it was the end of the Jurassic Period that saw the extinction of dinosaurs from the face of the Earth, but that's an erroneous misconception. Instead, this was a time of significant changes in the environment and subsequently in the variety of plant and animal species, which set the stage for the next and longest period of the Mesozoic Era, the Cretaceous Period. The Cretaceous Period was the time of the rapid development for the dinosaurs. Across the world, these ancient creatures have evolved into many impressive forms, each one fighting for dominance in the battle for survival. The Cretaceous was a time when some of the most awe-inspiring herbivores and most terrifying predators roamed the planet. Imagine a towering Argentinosaurus reaching a height of 7 stories. A formidable Carnivore Dinosaurs that looks even more threatening than the name suggests, or a heavily armored Ankylosaurus, armed with a club-shaped tail. None of these creatures were willing to give up an inch, and the competition never ceased, as there was an endless struggle for the right to survive. Only the strongest and toughest species could secure a place at the top of the food chain. But this great era of dinosaur domination ended abruptly and catastrophically with a truly harrowing event that led to the tragic extinction of most dinosaur species and forever changed the course of life on Earth. The end of the Jurassic Period marks the beginning of the Cretaceous Period, the final period of the Mesozoic Era. It spanned over a long period of time from 145 to 65 million years ago. During this time, many different types of dinosaurs developed on our planet, including some of the largest and most iconic creatures to ever exist. As the Jurassic gave way to the Cretaceous, dominant fauna began to change and new groups of dinosaurs, such as the ceratopsians and theropods, grew to carry increasingly more importance. The Cretaceous Period is divided into 2 epochs, Early Cretaceous and Late Cretaceous. The Early Cretaceous Period, which took place between 145 and 100 million years ago, saw the diversification of dinosaurs and the emergence of new groups such as ornithopods and sauropods. This was also the time when the first birds evolved from the small feathered theropods. The Late Cretaceous, which took place between 100 and 65 million years ago, brought even more dramatic changes to Earth. One of the most significant events of this time was the tectonic breakup of the Pangaea supercontinent into separate land masses of Laurasia and Gondwana, which ultimately led to the formation of modern continents. This created the conditions for the evolution of unique dinosaur fauna on every continent. New environment also led to the emergence of new types of dinosaurs, adapted to the specific conditions of their habitat. The Late Cretaceous was also the epoch that saw the appearance of the first flowering plants, which had a major impact on the ecosystems of that time, making changes to food chains and the ways dinosaurs interacted with flora. Furthermore, as sea levels began to rise, flooding low-lying areas and creating the shallow waters we see today, it gave way for the new marine ecosystems to develop. At the time, the aquatic life was bountiful and varied. As the Cretaceous Period went on, the continents began to slowly shift apart and take on their current form. The once unified landmass of Pangaea gradually gave way to the separate landmasses of Laurasia and Gondwana, and eventually the modern continents we know today. Due to this event, the dinosaurs that once roamed freely across Pangaea were now isolated on their respected landmass, surrounded by unique and distinctive flora and fauna. During the Cretaceous, the Earth was ruled by gigantic creatures, each with their own unique strengths and weaknesses. At the heart of the North American continent, a fierce battle was about to unfold between the most powerful predators and the most persistent herbivores. Tyrannosaurus rex, the king of the predators, roamed the land in search of his next prey. It was one of the largest land predators ever to have existed, reaching a length of 39 feet and weighing about 7 tons. Armed with massive jaws and razor-sharp teeth up to 6 inches in length, it was a formidable adversary for any creature it came across. The discovery journey of the Tyrannosaurus rex began at the end of the 19th century, when the first remains of this mighty predator were discovered in the western United States. This discovery was a milestone in paleontology, and as it was one of the most complete and largest dinosaurs to have ever been discovered at the time. The first specimen discovered was on display at the American Museum of Natural History in New York. The T-Rex had powerful jaws with a bite force of over 12,800 pounds, making it one of the strongest animal bites ever recorded. It's assumed that a T-Rex was also a fast runner, catching up to its prey. The T-Rex could reach speeds of up to 20 miles per hour. Triceratops, in turn, was one of the few creatures that could stand up to the mighty Tyrannosaurus rex. Triceratops was a large herbivorous dinosaur that looked somewhat like a modern rhinoceros. They reached up to 29 feet in length and weighed up to 12 tons. Triceratops had a massive head, with its skull making up a third of its entire body. It also had a bone frill around its head, and this frill was made of keratin and blood vessels similar to the feathers of a modern bird, and it suggests that, like the birds, Triceratops may have been sporting vibrant colors. The colors likely played an important role in socializing, as well as demonstrating the specimen's strength or signaling dominance to potential mates or rivals. Fossilized skulls of Triceratops have been repeatedly found with abrasions and dents, indicating confrontation with rivals, including predators and fellow Triceratops in the battle for territory or partners. One such specimen even had a broken horn and tooth marks, and they could be matched to a Tyrannosaurus rex bite. However, fossil studies have shown that the dinosaur itself died of natural causes. This shows that with its 3 horns and protective bony frill, the Triceratops was a formidable opponent for any predator. At the same time, a heavily armored Ankylosaurus roamed the land on the territory of the modern USA and Canada. It reached 29 feet in length and a weight of about 7 tons. The Ankylosaurus is also known for its distinctive body armor, which includes thick, bony plates and a club-shaped tail. This armor made the Ankylosaurus virtually invulnerable to predator attacks. In particular, the club-shaped tail was one of its most striking features. Formed from several large fused bones, it created a bone mass at the end of the tail that weighed several hundred pounds. And this mass was used as a defense against predators that could be swung with great force, breaking bones and even killing the attacker. This unique adaptation, along with its armor, allowed the Ankylosaurus to survive in an environment where predators constantly hunted for food. Another unique inhabitant of North America was the Pachycephalosaurus. In 1943, a paleontologist named Barnum Brown made the groundbreaking discovery of a skull in the Hell Creek Formation of Montana. The dinosaur reached 15 feet in length and weighed about 990 pounds. Its Latin name, meaning fat-headed lizard, refers to its most distinctive feature, a thick, domed skull up to about 6 inches thick, which was used for butting its head. This behavior could be used for courtship or to resolve territorial dispute. Despite this feature, Pachycephalosaurus were generally peaceful creatures, spending their time grazing in clearings and avoiding conflict. We usually think of dinosaurs as fearsome lizards, often huge in size. However, there were also very interesting species on Earth that had an atypical appearance. Let's fast forward to Laurasia, the second fragment of the once unified supercontinent Pangaea. In the dense primeval forest of the early Cretaceous period, there was a small feathered dinosaur known as Archaeopteryx. The Archaeopteryx was the size of a crow. It was one of the first birds to evolve from small feathered theropods. and it spent its days hunting insects and small reptiles among the branches of the ancient trees. The discovery of Archaeopteryx dates back to the late 1850s, when a German farmer named Jacob Niemeyer discovered a fossilized feather in the Solnhofen limestone formation in Bavaria, Germany. Over subsequent decades, more complete samples were found. The discovery of Archaeopteryx was significant because it presented the scientific world with the first clear evidence of an evolutionary link between birds and dinosaurs. Its unique combination of bird and reptile characteristics such as feathers and the wishbone challenged the conventional view of birds as a separate group of animals. Meanwhile, in a different end of the same woods, there was a chase. Leptoceratops, a ceratopsian dinosaur, was being pursued by a predator. Leptoceratops had a compact and agile body which was easily maneuvered, relying on 4 legs. In Greek, Leptoceratops meant thin-horned face. This animal had a sharp beak, a small frill on the back of the head, and a short horn on the nose. It was about 6.5 feet long and weighed approximately 330 pounds. Since this herbivorous dinosaur was relatively small, it could easily fall prey to other predators. Leptoceratops was chased by the fast Sauronothoides. Sauronothoides was a carnivorous dinosaur. It could reach up to 10 feet in length and up to 6.5 feet in height. They had an elongated skull which was compressed vertically. They also had a relatively large brain and sharp teeth. A large, formidable sickle-shaped claw on the second toe of each foot helped to grab its prey and most likely rip it open. With their deadly tool set, their victims stood almost no chance. Moving further east as we travel through our ancient world, we meet a variety of majestic creatures. These creatures once considered the vast expanse of Asia their home. From towering herbivores to the frightening predators, these leviathans had a myriad of adaptations that allowed them to thrive in their environment. The species that undoubtedly ruled over the territory of modern Asia was one of the most ferocious predators, the Tarbosaurus. Tarbosaurus was a large theropod dinosaur that belongs to the Tyrannosauridae family, which also includes famous dinosaurs like the Tyrannosaurus rex and the Albertosaurus. Tarbosaurus was a bipedal predator and one of the largest carnivorous species of its time. Scientists estimate that the adult specimen was about 40 feet long and weighed up to 6 tons. It had a massive skull with powerful jaws, long, sharp teeth, and strong neck muscles. These features made it one of the most formidable predators of its time, allowing it to kill large prey. Tarbosaurus was first described by paleontologist Rinken Barsbold in 1955 and given the name Tarbosaurus batar. It is known to have lived in the modern-day Mongolia region, where several well-preserved fossils of the species have been discovered. Tarbosaurus is considered a close relative of Tyrannosaurus rex, and some paleontologists believe that the two species are actually one and the same, with Tarbosaurus being an Asian species of Tyrannosaurus rex genus. However, most modern research suggests they were separate species, with Tarbosaurus having distinctive features such as longer arms, more elongated skull, and a less robust build than the T-Rex. Generally, Tarbosaurus could afford to snack on dinosaurs of any size as long as it reached adulthood. Those that were younger could only manage small creatures such as a Psittacosaurus. Psittacosaurus was a genus of small herbivorous dinosaurs that lived during the Cretaceous period. They were members of the Ceratopsian family, which also includes famous dinosaurs such as the Triceratops and the Styracosaurus. Translated from Greek, Psittacosaurus means parrot lizard. The name was chosen because the skull of the Psittacosaurus has a beak-like muzzle similar to a parrot beak. The shape of the skull and the position of the eyes suggest that the head movement of the Psittacosaurus were similar to those of parrots. The beak-shaped snout is a common feature among herbivorous dinosaurs that allowed them to effectively cut through vegetation. Psittacosaurus was a quadrupedal dinosaur, meaning that it walked on 4 legs, and was one of the smallest ceratopsians, measuring about 6.5 feet in length and weighing only 44 pounds. With a small skull, a beak-like snout, and flat, leaf-like teeth, it was able to feed mainly on soft plants. Psittacosaurus is also known for its unique cranial ornamentation, which includes an elongated skull, small horns, and a frill that may have been used for defense or to show off. Due to its unique skeletal structure, the dinosaur could move with great speed and agility, which may have helped it evade predators. The velociraptor was another famous predator that roamed this area. Unlike Tarbosaurus, Velociraptor was a pack animal. Velociraptors are known for their intelligence and herd hunting behavior. With their sharp claws and clever hunting tactics, they were a formidable opponent for any creature. The discovery of the Velociraptor happened in the early 20th century, when the first Velociraptor fossils were discovered in the Gobi Desert in Mongolia. In 1923, a team of paleontologists led by Roy Chapman Andrews of the American Museum of Natural History discovered the first fossils of a Velociraptor in the Jadhota Formation. The specimen was the first scientifically recorded Velociraptor. It was given the name Velociraptor mongolensis. Over the following decades, an increasing number of Velociraptor fossils were found in Asia. Velociraptor was a feathered dinosaur. This discovery was made as a result of finding fossils with feather impressions on the arms and tail. The name Velociraptor comes from the Latin words velox, meaning quick, and raptor, meaning thief or robber. The name was chosen because of this dinosaur's speed and agility, as well as its potential as a predator. The smaller size of Velociraptor, about 6.5 feet long, weighing about 33 pounds, as well as the features of its skeleton, such as a large sickle-shaped claw on the second toe of each foot, suggests that it was a highly dexterous and active hunter. This claw was probably used to catch and hold prey, such as small dinosaurs and early mammals. Velociraptor is known for its intelligence and hunting behavior, which is unusual for dinosaurs. Velociraptor had a relatively large brain relative to its body size, suggesting that it was an intelligent and highly adaptable predator. It's believed that they hunted in packs and may have been able to communicate and coordinate hunting strategies with each other. A fossil of Velociraptor mongolensis and Protoceratops andrewsi was found at the Gobi Desert of Mongolia in 1971. It was called the fighting dinosaurs. The skeleton showed 2 dinosaurs in battle with one another, forever imprinted in stone. The Velociraptor specimen is a sub-adult, and it was preserved with one of its hind legs holding onto the frill of an adult Protoceratops. Protoceratops specimen was also preserved with its mouth open, suggesting that it had bitten a Velociraptor at the time of death. The discovery provided important data about the behavior and ecology of these 2 dinosaurs. The position of the skeleton suggests that the 2 animals were fighting at the time of death, possibly over territory or food. It also suggests that the Velociraptor was an active hunter and opportunistic predator. That means that it would use any available prey that comes its way rather than having a specific preference or diet. It also suggests that the Protoceratops was able to defend itself against it. Protoceratops was an herbivore dinosaur that lived during the late Cretaceous. It was a quadrupedal dinosaur, one of the smallest ceratopsians, reaching 8.2 feet in length and weighing about 176 pounds. Its skull was enhanced with strong jaw muscles and leaf-shaped teeth, suggesting it lived mainly on a diet of soft plants. Protoceratops had a beak-like snout and a distinctive skull that it was adorned with a large bony frill on the back, with a pair of small horns above the eyes and a pair of large horns on the cheeks. The frill was likely used for showing off or defense. Our next location is the land of modern Africa. A group of the Spinosaurus, large carnivorous dinosaurs of that time, they hunt for food in the mangroves on the banks of a huge river. Spinosaurus was one of the largest carnivorous dinosaurs that lived during the Cretaceous period. It was longer than a Tyrannosaurus rex and a Giganosaurus. Its length was estimated at up to 60 feet with a weight of up to 20 tons. Spinosaurus is known for its large sail-like feature on its back made of elongated nerve spines. The function of this feature is still debated by scientists, but it is believed that it could have been used for thermoregulation, courtship, or simply to appear more intimidating. Spinosaurus led a semi-aquatic lifestyle. They could swim and hunt in the water thanks to their webbed feet. Their long, narrow jaws were studded with large, sharp teeth and were perfectly suited for holding slippery prey trying to escape, such as fish or amphibians. Spinosaurus was a rather sizable animal with large frontal limbs, armed with long, sharp claws, which likely played an important role in holding and killing the prey captured using their teeth before swallowing. On another shore, there's a group of iguanodonts, large herbivorous dinosaurs grazing the lush vegetation along the riverbank. Iguanodons were large herbivorous dinosaurs that moved around on all four and also presumably two legs. They were about 32 feet or 10 meters long and weighed about 4 tons. They had big, narrow heads, a keratin beak at the front of the jaw, filled with teeth similar to those of an iguana, but larger and more frequently placed. One of the best-known features of the iguanodon is the spike on the thumb of the forelimb. It's believed they could use it to inflict powerful blows on predators. Speaking of predators, in the same area, giant Carcharodontosaurus roamed in search of prey. Carcharodontosaurus was one of the largest carnivorous dinosaurs of its time and probably one of the top predators of the Cretaceous period in Africa. The length of his head alone was 63 inches. The total length, according to various estimates, could reach up to 39 feet, and its weight varied from 6 to 15 tons. Carcharodontosaurus was bipedal and had a long, heavy tail to help them balance the body. It was truly a formidable predator. Their teeth reached 8 inches in length. Carcharodontosaurus got its name for its serrated teeth, which were similar to those of a great white shark, the Carcharodon, which is why it is also known as the great white shark lizard. It's unlikely that any prey was able to stand against a Carcharodontosaurus specimen on its own. The dinosaur could feast on both Spinosaurus and Iguanodon. Now, let's talk about the real giants. The Hinkle Formation in South America has become famous for its large number of dinosaur finds of truly colossal proportions. Of course, our list starts with the Giganosaurus. Giganosaurus, one of the largest known carnivorous dinosaurs, which according to some estimates could have been even larger than the famous Tyrannosaurus rex. But Giganosaurus was a slow-growing dinosaur that took somewhere between 20 to 25 years to reach full adult size, a time frame much longer than the T-Rexes. An adult Giganosaurus was about 43 feet long and weighed up to 11 tons. Giganosaurus fossils have been found in Argentina, making it one of the best-known carnivorous dinosaurs from South America. This discovery supports the idea of a rich fauna and diverse ecosystem on the Gondwana continent during the Cretaceous period. Some research on social behavior suggests that Giganosaurus may have lived in groups similar to other theropod dinosaurs. This may indicate that it was a social animal that hunted in packs. But the Giganosaurus was not the only predator in this lush tropical environment. Competition among carnivorous dinosaurs was fierce. Giganosaurus had to fight for territory and resources, not only with each other, but also with other carnivorous dinosaurs, such as the Maposaurus. The Maposaurus is closely related to the Giganosaurus. It was similar in size, shape, and feeding habits, and both were large carnivorous dinosaurs living in South America during the late Cretaceous. And both had similar structures of the skull and jaw. Maposaurus was a large carnivorous dinosaur about 36 feet long and weighed up to 5 tons. The first remains of a Maposaurus was discovered in Argentina in 2000. Multiple specimens were found together, which is quite rare in dinosaur fossils. The discovery of multiple specimens suggests that Maposaurus was a social animal living in groups and working together to hunt large prey, much like modern wolves or lions. This unique behavior among theropod dinosaurs was a very important finding for understanding dinosaur social behavior. Speaking of Argentina, we have to mention the largest dinosaur of the Cretaceous period. In fact, this dinosaur was one of the largest known dinosaurs to have ever existed. We're talking, of course, about the Argentinosaurus. By some estimates, Argentinosaurus may have reached 115 feet in length with a total weight at about 100 tons. As a sauropod, the Argentinosaurus was an herbivore and likely fed on a variety of plants, including conifers and ferns. Its long neck and small head were adaptations designed to reach the highest branches of trees. As a large sauropod, Argentinosaurus was a slow animal, but its large size made it relatively impervious to most predators. They had a unique limb structure with very wide hips and short thigh bones. This suggests they had a wide stance, and that was in order to support their massive weight. Growth lines found in the bones of Argentinosaurus suggest it had a long lifespan, potentially living up to and over 100 years. This lifespan is much longer than most other dinosaurs, most of which live between 20 and 50 years. Over millions of years throughout the Cretaceous, Australia gradually separated from Gondwana and began to shift north. The continental drift caused Australia to move away from Antarctica and eventually collide with the Eurasian plate, forming the Australian continent as we know it today. The climate of Australia at that time was generally warm and humid, with lush vegetation covering much of the landscape. Within the continent, there were abundant systems of rivers and lakes. Climate in the region was seasonal. The dry season gave way to the rainy season. This had a significant impact on the dinosaurs inhabiting that region, as they had to adapt to changing conditions in order to survive. The large herbivorous Muttaburrasaurus grazed on the lush vegetation heavily present in the region. It was a quadrupedal dinosaur with a massive body and a small head. Muttaburrasaurus was a large dinosaur estimated to reach up to 26 feet in length and weighed around 3 tons. Muttaburrasaurus fossils have been found in several different locations throughout Australia, suggesting this dinosaur had a wide range and lived in isolated populations. Muttaburrasaurus had a number of features that allowed them to survive in arid seasonal climates, such as their large nasal passages that helped to reduce water loss. As an herbivore, Muttaburrasaurus fed on a variety of plants, including conifers, ferns, cycads, and ginkgos. During drought seasons, however, these dinosaurs had to migrate to new locations in search of food and water. Unlike our next ornithischian herbivores, the Lielanosaur. Lielanosaur was a genus of a small, bipedal, herbivorous dinosaur that lived during the Cretaceous. Paleontologists estimate it was no more than 4 feet in length and weighed about 44 pounds. Their small size, as well as the fact that the Lielanosaura were bipedal, allowed them to move quickly and nimbly through the undergrowth in search of food. The Muttaburrasaurus and the Lielanosaura lived in the same ecosystem, but differences in their size and other characteristics allowed them to draw on different resources and avoid competition. In the early Cretaceous, Australia was much closer to the Arctic Circle. This resulted in very long nights and days. Depending on the latitude, it's possible that some places didn't see the sun for weeks or even months at a time, meaning that a Lielanosaurus had to live in darkness during winter. A skull fragment from Lielanosaurus show enlarged eyes and proportionally large optic lobes, indicating their adaptation to low-light conditions. Lielanosaur also had long, thick, fur-like bristles on their body that helped keep them warm during the cold and dark polar nights of Gondwana during the early Cretaceous. Additionally, this dinosaur's small size reduced its need for water during dry seasons. Our story should give you a general idea of where dinosaurs lived in the world during the Cretaceous period. It's worth mentioning that some of the dinosaurs we've listed could have been found in other places than the ones we indicated, since the continents themselves were different in the late Cretaceous due to the movement of tectonic plates during this period of time. In conclusion, the Cretaceous was a time of great diversity of dinosaur evolution. From the huge Argentinosaurus to the small, agile Lielanosaura, a huge variety of species flourished during this time. However, the Cretaceous period also marked the end of the dinosaurs' reign on Earth. A global extinction caused by a meteorite impact, according to one theory, destroyed the dinosaurs along with many other species that existed at the time. This tragic event marked the end of the era of dinosaur rule, but it also opened the door for the emergence of mammals and other animal groups, which ultimately led to the diversified life we see on Earth today. Once again, our planet reminded us that change is the only constant, and life is incredibly fragile. But we can still theorize what would have happened if the Cretaceous Paleogene extinction had not taken place, and the dinosaurs had not met their death. What would the world look like today? Would the evolution of humanity taken a different path, or would man have remained the apex predator on planet Earth? A cataclysm caused by an asteroid impact, more precisely, the Cretaceous Paleogene extinction, became a turning point when one domineering species is replaced by another. Because death is always the beginning of a new life for someone or something else. But what took place of the giant reptiles first? This is where we come across our first pitfall, faced by everyone who took interest in the fate of dinosaurs. Many people think that the asteroid crash resulted in all dinosaurs becoming extinct within 1 or 2 days after the impact. But that's far from the truth. The species that were outside of the 900-mile zone of instant destruction had to face challenges. Huge tsunamis reaching 300 feet in height, endless forest fires caused by the flow of scorching hot air, and trillions of tons of earth and rock launched into the atmosphere, making the planet practically uninhabitable. But the actual extinction is a very long process. At first, the planet was launched into almost complete darkness. Trillions of tons of dust and soot lifted into the atmosphere, shielded the planet from sunlight for literal years. Furthermore, research indicated that the first 600 to 700 days after the impact, the dust concentration was so great, the sky was entirely covered. An eternal night of sorts, except without the moon or stars. As a result, the lack of photosynthesis, which in a very short time killed most of the plant species, including the royalty of the flora world at the time, the ferns, which in itself is already a terrible ecological catastrophe. But perhaps the main consequence of the remaining living beings was the global cooling. The thing is, the Yucatan Peninsula that sustained the impact of the asteroid has been and still is rich in minerals containing sulfur. As the sulfur aerosols lifted into the atmosphere, they practically turned it into a climate blanket, preventing the energy generated by the sun to heat the surface of the earth. This type of darkness continued for years, but the actual cooling has only happened for a short period. From the geological point of view, only 1 million years, but during this time it significantly influenced the species diversity on the entire planet. Now let's get our facts together. The long and very destructive night that killed the majority of nutritious plants resulted in the large part of herbivorous dinosaurs being on the edge of extinction, which in turn meant these large predators started losing their source of food, which made dinosaur extinction just a matter of time. It isn't known exactly when the very last dinosaur died, whether that was a few decades or 500,000 years later. We know one thing for sure. Between the start of extinction and the end of planet cooling, all large animals have disappeared. We're talking about anything weighing upward of 55 pounds. This number is more nominal, but it reflects the fact that beings with larger body mass and faster metabolism just couldn't find enough food to sustain them. The era of giant lizards was steadily coming to its end. But what came next? The most sophisticated viewers might say it was mammals. Small, savvy creatures that in the dinosaur era rarely surpassed the size of a mouse conquered the world. But it's not quite what happened. The truth of the matter is any significant climate event rearranges the food chain. However, the unbearable living conditions and the absence of available food resulted in surviving organisms forming isolated enclaves where life slowly developed and evolved on a relatively small scale. This way, the space at the top of the food chain remained vacant after the fall of the dinosaurs for the next 15 million years. That's how long it took for the planet's ecosystem to restore and enable larger creatures, including mammals, to exist. Only after some time, when significant areas of Earth have changed from dense jungle to sparse forest, life out in the open contributed to mammals increasing in size. Before that, all of our mammal ancestors were small, omnivorous beings, something between rodents and lizards. We deliberately highlighted their omnivorous diet. It was one of the key factors that resulted in their effective survival. It's worth noting that the first therapsids, which was the name given to the first proto-mammals, didn't come to existence after the dinosaurs, or even at the dawn of their existence. Formerly, they branched off the Pelycosaur species, which was a common ancestor of mammals and dinosaurs 272 million years ago. This is what our common ancestor looked like, by the way, which over time evolved into something much more familiar. For millions of years, mammals were at the bottom of the food chain, becoming prey to larger and more aggressive tetrapods, the dinosaurs. However, the asteroid made some changes over the next few million years, and slowly but surely mammals filled the vacant population niches, predominantly on the ground and next to large bodies of water. Only a few managed to get established in the air or in the deep water. But why? Up there, animals had their own special struggle for a place under the sun. It's particularly telling that the sky is the only environment where the only direct relatives of dinosaurs known as Maniraptorus has survived. A small number of them managed to survive, and over the next 15 million years, produce the offspring resembling modern birds. That might strike you as odd. A pigeon or a penguin didn't look very similar to a T-Rex, but the connection is there, right down to the bone structure. When the extinction occurred, the traits developed by birds over millions of years became the deciding factor in their survival. Entire groups of avians, including the toothed birds known as the enantiorniths, became extinct. It's unlikely that only one trait decided their fate, and yet survival in a mass extinction event often relies on luck, and the beak was like an ace for some birds. By the end of the Cretaceous period, birds with a beak had a more diverse diet than their toothed counterparts. These birds didn't focus on insects or other live prey, which enable them to harvest seeds and nuts. When the animal world has significantly reduced in size because of the extinction event, this type of food allows the beak birds to survive the hard times. What's funny is that today the closest direct relative of the dinosaurs, that's the creature that underwent the least change on the chromosome level, and that's a chicken. So if you want to have a short tour into the fauna of the Cretaceous period, and observe the way real dinosaurs used to act, take a look at the nearest chicken coop. But if you want to know what the first birds looked like, you should take a trip to the Amazon rainforest. The only living representative of one of the oldest avian species that originated 64 million years ago is the Hoatzin bird. If you take a close look at this incredible bird, the resemblance between a Hoatzin and the reconstructed model of a semi-bird, semi-reptile creature, created based on excavated bones. Young Hoatzin birds have an interesting vestige inherited from the proto-birds, namely the two claws on the bones supporting their flight feathers, kind of like hands. If the baby bird falls out of the nest, which is a common cause of death for a young bird, the Hoatzin offspring can use the claw to get to safety. The mass extinction affected the deep blue seas too. Down there, the extinction created vacancy for the unique species niches. The world's oceans experienced their own revolution, where the monstrous mosasaurs and megalodons were replaced by fish. More precisely, ray fin fishes or actinopharygi, named for bony spines on their fins arranged like rays of light. Again, the ability to quickly adapt to the new situation played its part, just as it did with the protobirds. Today, the ray fin fish make up over 95% of all fish species known to science. The fish were gradually taking over the sea just as the mammals took over the land after dinosaurs went extinct. Scientists quote the disappearance of the majority of the ammonites as one of the main reasons for the successful population of ray fin fish. Ammonites are the relatives of the modern calamari, octopi, and other cephalopods. They were a very prolific species and insatiable customers of tiny plankton, which was the main food supply of regular fish. In a way, they presented as much danger to the fish as giant water reptiles. The sequence of events that triggered their extinction is very simple, not unlike what happened on land. Due to the absence of photosynthesis, the large number of phytoplankton, which feeds the regular zooplankton, had died. And without it, supporting the voracious population of ammonites was simply impossible. It is interesting that when studying the fossils from that time period, the scientists discovered that the population of ancient cartilaginous fish, which includes species like sharks and rays, didn't suffer a significant reduction in size. We can't know for sure, but it appears that the sharks did not pose a serious danger to the ray fin fish, which allowed the latter to fill almost all the vacant niches. Perhaps it's due to its relatively small population size. Whatever it was, this baby boom in the population of ray fin fish was so significant, it became known as the new era of fish. Why new? Because at one point, the water-dwelling dinosaurs already took this title from the sharks. The first fish era took place during the Devonian period, which lasted from 417 to 354 million years ago. This is when the first fish came to exist, including sharks and rays. This new era of fish lasted for at least the first 24 million years of the Cenozoic Era, which followed the Triassic Period. And after this, fish made space for certain mammals, such as whales and cachalots, that decided to venture into the water. To this day, ray fin fish are the most diverse water-dwelling vertebrates. While other animals may seem larger or more advanced, fish are still the most predominant species in evolutionary terms. But let's get back to the land, where yet another fourth evolutionary battle for survival was happening at the time. Despite the vast diversity of gymnosperms, mostly evergreen plants, and ferns, their heyday is suddenly interrupted at the end of the Triassic Period. At the same speed as the gymnosperms disappeared, the flowering plants entered the arena. Let's take a look at how it happened and how it affected the evolution of the animal population during the Cenozoic Era. The thing is, ancient species of gymnosperms and ferns were designed to exist in a wet climate. And when they found themselves in unsuitable living conditions, they quickly started to die off. All the while, the young species of flowering plants managed to adapt to the new environment and quickly took over the land. One of the main factors in the victory of the flowering plants was the development of so-called double fertilization, which contributed to their vitality and adaptability to the new environmental conditions. The transition from gymnosperms to flowering plants was without exaggeration one of the most important leaps in the history of plant life. Their evolutionary fight for survival radically changed the face of plant life on Earth and caused a real revolution in nature. The gloomy and monochrome forest made up of gymnosperms and ferns were replaced with flowering plants, diverse in both shape and color. Besides, the flowering plants created a more nutritious, undoubtedly better food supply for the animals. Around the same time, during the Cenozoic Era, the first grain plants came to exist. As such, the evolution of many animal species revolved around their interaction with the first flowering plants. The entire groups of living beings, such as carnivorous and seed-eating monkeys, could continue living surrounded only by flowering plants. In turn, animals became the most effective method for transporting fruit and seed across long distances. The influence of flowering plants was so great, we can confidently state that they played a major role in the development of great apes, and consequently you and me, people, Homo sapiens. The Cenozoic Era is an incredible period in Earth's history. It was as if the crash of the asteroid destroyed a colorful puzzle where giant reptiles ruled the world. After breaking into a million pieces, the puzzles came back together but revealed an entirely new picture, where you can clearly see the remnants of the past. This is the era of amazing creatures that look like they came directly from ancient myths and tales. The saber-toothed Metatherian tiger called Thylacosmolus that reached the size of a jaguar. The walking whale known as Ambulocetus, which only 20 million years later, after the catastrophe, would finally come to live under the water, reproducing descendants like orcas, whales, and cachalots. The saber-toothed elephant, Deinotherum, and the hippo ancestor that looks more like a giraffe, known as the Paraceratherium. That's just a fraction of the species diversity that expanded in such an explosive fashion, allowing the mammals to take the key position in the food chain. Though this tight and mutually beneficial interaction, the flora and the fauna revived after a global cataclysm that destroyed the vast majority of life on this planet. The Cenozoic Era marked the end of existence for some species, gave way to others, more complex and diverse organisms, confirming yet again the cynical yet endlessly true theses that death is not the end, but the beginning of something new.